Here we're going to be talking about the steps that lead up to muscle contraction. We start with an impulse traveling down the axon towards the axon terminal. And this impulse is in the form of sodium ions entering the axon in waves all the way down until you reach the synaptic end bulb here at the end. Once the nerve depolarizes, the motor neuron depolarizes, that triggers calcium to enter through these voltage-gated calcium channels, which in turn triggers the exocytosis of acetylcholine that's held in these vesicles. This acetylcholine exits the synaptic end bulb, crosses the synaptic cleft, and binds onto receptors on the motor end plate. Once it binds to these receptors, they change configuration, and since they are also sodium channels, they allow sodium to pass into the muscle cell. This in turn triggers the depolarization of the muscle cell, which also travels down in waves, allowing more and more sodium to enter the cell, depolarizing the muscle cell. Once the sodium enters the muscle cell, it triggers the calcium channels in the sarcoplasmic reticulum to open, which allows calcium to exit the sarcoplasmic reticulum and enter the muscle cell. We're going to go look at a sarcomere now. And we've got all the structural components of a sarcomere here, starting with the ends, which are the Z line on both sides, or a Z disc. Then we also have the M line here, M for middle, and that's a structural component that helps the sarcomere return to its length and shape after contraction. Out of the Z line, you have actin filaments. These are your thin filaments, and they're going to come out both sides into two separate sarcomeres. In the center, you've got the thick filaments, the myosin filaments, and then you also have titin, another structural protein, which attaches, let's see if I can spell it right here, attaches to the Z lines and travels through to the M line. And this is what gives the sarcomere its elasticity and specifically allows it to return to its length and shape after contraction. This middle band here, that's composed of only thick filaments and does not include the overlap of the thick myosin and thin actin. This middle band is your H band. Your striation that you're going to see in your slides includes the entire area of the thick filament, which also includes some of the overlap of the thin filament. This is your A band. And this is the letter A for dark, so it's the dark band that you're going to see on the slide. And it's the striations. And then lastly, you have your I band, and that is composed of only the thin filaments. I for the word light, and it's going to be the closest to the Z lines and actually extend through to the other side of the Z line. So I know the proportions aren't right here, but the Z line is going to be right in the middle of your I band, since your I band extends on both sides of the Z line. The M line is going to split the H band and the A band down the middle. So then we're going to move over here to simply an actin filament. And these yellow balls you see are your actual actin proteins. And this is also bound to your troponin-tropomyosin complex. And this is your troponin. And these strands are your tropomyosin. And in the resting state, the tropomyosin is covering up the binding sites, the myosin binding sites on the actin. So the myosin can't bind to it. Once your muscle cell depolarizes, and there's calcium floating around that came out of the sarcoplasmic reticulum, this calcium is going to bind to the troponin, which is going to change the structural configuration of this protein complex, which in turn moves the tropomyosin out of the way and allows the myosin to bind to the actin. And this requires no ATP. The myosin just wants to bind to the actin. The ATP is required to ratchet the myosin head, which pulls the actin in that sliding, whatever she called it, the sliding complex or the sliding motion. But once these heads ratchet, it's going to pull the actin and therefore the Z lines closer to the M line. And then another ATP is required to release the myosin from the actin. And remember that some myosin heads are still bound even when others release. And this is what's going to hold it in place and allow it to stay as contracted as it is until more heads can return to their normal configuration, bind back onto the actin, and use another ATP to ratchet again, and again bring the Z lines closer together, thus shortening, contracting the sarcomere, which in turn contracts the entire muscle as the sarcomeres go, through the entire myofibril. Once the nervous impulse is finished and is no longer coming down the axon down the axon towards the synaptic end bulb, it's going to shut off the stimulus. Acetylcholinesterase is going to break down any acetylcholine that's found in the synaptic cleft, so it can no longer be used. Once this happens, the sodium-gated channels are going to close. No more sodium is going to come into the cell, and you're going to have active transport of sodium out of the muscle cell back into the extracellular fluid via active transport in the sodium pumps. And once the sodium is out of the cell, you're going to have the same thing happen to the calcium. It's going to come back into the sarcoplasmic reticulum via active transport, and this is going to repolarize the muscle cell back to its negative resting state. And the calcium is no longer bound to the troponin here, which means that the tropomyosin goes back to covering up the myosin binding sites. So myosin can no longer bind to actin, and the sarcomere is going to lengthen back to its original shape because the titin here is going to want to pull the Z lines back to where their original position is. And that is your basic steps of muscle contraction.